Okay, good morning. This is Professor David J. De Los Reyes. My session for this morning will be a long video format discussion on AC circuit, and we are now on lesson number 7. Okay, let's proceed. This is a new topic. It is in sequence with the, what I call this, syllabus of an AC circuit. Okay, let's proceed. Alternating current circuit, lesson number 7. The title of the topic is voltage calculations for impedance. Okay, initially we studied impedance. Okay, we performed the fundamental operations on how to convert rectangular to polar or polar to rectangular. Then after that, we go with the so-called, what you call this, computation of current, considering impedance. And for tonight, or for this morning, our topic will now be the voltage calculations for impedance. If an impedance is connected to an alternating current circuit, how could we compute the individual voltages, like the voltage across a resistance, voltage across a coil or a motor, or voltage across a capacitor with respect to the total applied voltage? There should be a relation of the applied voltage with respect to the individual parameters. So for this morning, we will now try to derive and what will be the relation and how we will figure it out using the vector diagram. Because it is very important in the calculation of the power splitter, meaning the power consumption. It's a must that we know how to calculate current and individual voltages for all the circuit parameters. Okay, let's proceed. We are given a voltage source here. Okay, and the impedance connected is a resistance, a coil, or a motor maybe, an X sub C, a capacitor. It could be a synchronous motor that is overexcited, and it is to be considered meaning the current of that will be a leading current like an X sub C. So this X sub C here, it could be a synchronous motor that is overexcited. Okay, let's proceed. We will derive the relation of E with respect to the voltage across the resistance, inductance, and B sub C. To derive the equation, okay, if we try to take the total impedance of this, Z is equal to R plus Jx sub L minus Jx sub C. Okay, meaning the total impedance of the circuit here will be R plus Jx sub L plus Jx sub C. This is with the J, but it should be plus. This is with the J, but it should be minus. Okay, so we derive this equation here by taking the total impedance of the circuit, considering that there are some parameters which are real and there are parameters which are imaginary. So we must have to place the so-called proper designation. So Z is actually R plus Jx sub L minus Jx sub C. Okay? Multiplying all the terms by I. Okay? There will be a circulating current whether we like it or not, right? So from the equation of the impedance, if we try to multiply that by I, okay, I multiplied by Z equal to the right hand side, I times the quantity R plus Jx sub L minus Jx sub C. Okay? Performing the operation, I times Z will be IC. We will distribute this one. It will be the so-called distributive law under college algebra. So we take the individual product of this with respect to the quantity. I times R will be IR, and I times plus Jx of L will be plus J times I times X of L, and I times minus Jx of C will be minus J I X of C. Okay? Then we will try to place a legend over here that the product of the total current times the total impedance is actually the voltage of the utility line. Right? And the product of current times the resistance is actually V sub R, meaning the voltage across the capacitor. Right? That's V sub R. The product of I times X sub L, okay, that will be V sub L. Right? It is the voltage across the inductor or coil. That's V sub L. Okay? What's next? The product of I times X sub C is the voltage across the capacitor. That is V sub C. In this computation here, we use absolute values. Okay? We are just taking for the meantime the magnitude. Okay? So in general now, if we go back to this, IZ is actually E. The product IR is actually V sub R. And the product the product of I X sub L is actually V sub L. So this is plus J V sub L. And the product I X sub C is actually V sub C. So this is minus J V sub C. So this is now the so-called voltage source in terms of the voltage across the resistor, inductor, and capacitor. This is in volts. And this is in, what do you call this? Rectangular part. Rectangular, okay? Real part, imaginary part, so it is in a rectangular part. If we try to bring out the vector diagram, how we will bring out the vector diagram of this? Because the voltage of the source is supposed to be a vector diagram. A vector, it got a magnitude in an angle, right? So if we try to bring out the vector diagram, for V sub R, it is a plain real part. So this is the value of V sub R. And plus JV sub L is actually upward. And minus JV sub C is actually downward. Okay? So for the voltage E, there will be three possible cases that will come out. Okay? That is case number one, that is when the voltage across the inductor, is greater than the voltage across the capacitor. If we try to add this one, they are both imaginary, right? But if this is bigger, whether we like it or not, the resulting imaginary voltage will be upward. Okay? Because V sub L is greater than V sub C. So there will be a resulting, right triangle that will come out, in which the real part is actually V sub R. The imaginary part is plus J, the difference of V sub L minus V sub C, with the condition V sub L is greater than V sub C. That's why we know that the direction of the imaginary part is upward. It is because V sub L is greater than V sub C. And for this, if we got the horizontal component and vertical component, okay, the sum of this plus this, vectorially, right, should be E. It is equal to the applied voltage. And there should be an angle theta over here. Okay? So if we try to bring out the equation of this, okay, E should be equal to V sub R plus J V sub L minus V sub C volts. That's case number one. For case number two, if the voltage across the capacitor is greater than the voltage across the inductor, meaning this is bigger than this. Okay, what will come out will be a right triangle that goes downward. This is B sub R. Since B sub C is greater than B sub L, the resulting real part should be downward, right? So this is minus J, B sub C, minus B sub L. Right? So this is the resulting imaginary part. This is the resulting real part of the voltage. And the voltage of the source will be the vectorial sum of B sub R plus this. So the resulting equation will be E will be equal to B sub R minus J times the quantity X sub C minus X sub L volts. With the given condition, B sub C is greater than B sub L. So we are adding these voltages here vectorially to get the applied voltage. You cannot just use the plain or the so-called plain algebra in which we are only adding maybe real numbers. And here we are adding real numbers with respect to an imaginary number. So if we try to add it, okay, we will use the so-called triangle method. We will be using the hypotenuse method, right? Because this B sub R is not the same as this JB sub L here. Because this is real and this is imaginary. So to add it, it will be a different thing. So use your knowledge on the so-called conversion from rectangular to polar or polar to rectangular. Okay, that's why from the previous lessons, okay, I give you the topic on how to convert real to polar or polar to rectangular. And this is in a rectangular form, also in rectangular form. Okay. For case number 3, this will be the so-called, that is when the power factor of the system will be unity. That is when the voltage across the inductor is equal to the voltage across the capacitor. If the voltage across the inductor and the voltage across the capacitor are the same, they will try to cancel out each other, right? So it seems our load is just a pure resistance. And that is what utility companies would like us to do. Okay, this voltage here should cancel out with this. So it seems we are only having a load that is lighting load. But in reality, we got a motor load and some other X sub C load. Okay? Unluckily, they were equal. That's why during this time when they are equal, our current consumption will be less. And our power bill will be less. And that's what utility companies would like us to do. Okay? So for case number 3, if B sub L is equal to B sub C, okay? E originally is actually B sub R plus JB sub L minus JB sub C. But if they are equal, this will try to cancel out. So meaning the imaginary part of the applied voltage will be 0. This is they are equal. So it seems we don't have an X sub L and X sub C, but in reality there is. They are performing a job, but what comes out is that they were equal, right? Meaning the power factor of the system is unity. Okay. So for case number 3, E will be equal to B sub R plus G0 volts. Okay. And if you try to bring out the vector diagram of the voltages, the component of P is just B sub R, and the imaginary part is 0. No upward, no downward, it is 0. So actually, we do not have a right triangle. What is only coming out is just E is equal to B sub R, a horizontal part. So actually, this horizontal part is less than this and also less than this. Okay? So it seems our system is actually very efficient. That is so when B sub L is equal to B sub C. Okay, so this is the vector diagram of the voltage equation E equal to B sub R plus G0 volts. Okay, this is the best scenario that will come out for any system, that is B sub L is equal to B sub C. Okay, because the current consumption during this time will be less, okay, and what we will be paying to the utility companies will be less, okay. Oh, that's it, guys. That's how we brought out the relation of the voltages for the three possible cases of load under alternating current circuit. Okay, I will repeat it for the last time before we go for this morning. Case number 1. Okay. When B sub L is greater than B sub C, this should be the vector diagram. This should be the voltage. For case number 2, when B sub C is greater than B sub L, this should be the vector diagram of the voltages, and this is the equation. And for case number 3, the base scenario for a system. That is when B sub L equal to B sub C, they try to cancel out. So meaning to say the utility voltage is just equal to the voltage across the resistance. Okay? This is a lesser value than the hypotenuse. So this is the best condition for any system. Okay, good morning from Los Angeles. This is Professor David J. de los Reyes.